Okay, so I am Soumya Chakraborty, an assistant professor of the Department of Statistics at Bethune College. Today I am going to talk about this topic, statistics as a technology in the 21st century. This talk will be more or less about the subject statistics, its basic philosophy and methodologies, and finally its applications in real life problems in different fields like technology, economics, finance, social science, and even in literature. And this talk will be for mainly for general audience. That is, more mathematical or statistical rigor will should not be expected from this talk. Okay, so I am very grateful that I am given this opportunity, and I like to thank the authority of Bethune College. So let's start. So this will be the more or less the content of this talk. First, I will introduce the subject statistics for general audience, and then what is statistics, what are the methodologies used in statistics, and then I will go to which is the main theme of this talk, the applications of statistics in different fields, and I will mainly talk about some of the very popular applications of statistics nowadays, mainly in technological fields like image processing and its application in medical imaging related to MRI, then pattern recognition, then a very vast branch of applied statistics called biological statistics, which contains medical statistics and statistical genomics, then econometrics and finance, another very important uh, field of research. Then I will finally conclude this talk with a topic that is called data science. Actually, we are introduced with this topic more or less now with this subject, and mainly in corporate sectors, data science is one of the key skills one need to join a good job in either in the IT, that is information technology, or in other corporate sectors. And even many of the institutes have introduced master degree courses or diploma courses in data science, and many of us know that this data science is more or less related to statistics. But what is the difference of data science with statistics, if there is any difference, of course? And if there indeed there is any difference, then what is the relation between statistics and data science? Will data scientists, will statisticians be transformed into data science in the next 15 years? That will be a very intriguing question to discuss about. So let's continue. So first of all, I need to uh, introduce the subject to general audience, that what is statistics. Actually, it's not a subject which we study in high school, at least up to class 10, at least in India. I do not know about other countries, probably not. We nowadays that is in the last 20 years, the syllabuses of mathematics up to class 10 have been rebuilt in such a way that some basic themes of statistics are already introduced in class 8 or class 9, but it's basically a subject which is not offered in the high school level, at least in the West Bengal or India. The study of statistics starts in graduate level, that is BSc level, and it's basically a mathematical subject. So what is the main aim of or main goal of statistics? So basically, statistics is the kind of computational science which aims to extract information from data and analyze that data and reach meaningful decisions based on that. Now, several questions arise from this. That what first of all, what is data, or what are data? Because we don't know whether data is plural or singular. Typically, data is used as a plural term. The corresponding singular term is datum. That means a single piece of information. So, what is data, and what are the mathematical tools of statistics? We have I have just told that statistics is a collection of mathematical tools. So what are those mathematical tools, and what are data? What data means? And finally, we have already studied about theoretical and experimental sciences like physics and applied physics, chemistry, industrial chemistry, biology. But for at least for the last 30 years, there is another paradigm of basic science which is called computational paradigm of science. And statistics is basically uh, is one of the representatives of that group of science, of that paradigm of science. So what is computational paradigm? That is another question. So I will try to answer these questions one by one. So first of all, we need, and there will be another question that we, at last, I have told that statistics tries to reach a meaningful decision. So what kinds of decisions are usually made based on statistical techniques and methods? So let's start. Okay. So first of all, what is data? So data means information about some attribute. It can be anything. It can be anything. The term data is usually in the plural sense, as I have already told. The corresponding singular term is datum. And so let's first understand about some let us see some examples of data. So suppose heights and weights of 100 students in a class, say class 9, or daily rainfall in Kolkata in centimeter or in millimeter for the month of July in 2022. This is just dummy. So it may be our hour-wise data, it may be daily data, it may be yearly data, and then daily number of road accidents at some point, let's say Shambhajar 5 point crossing in the last year, number of corona affected patients in different days during April 1 to May 31 in 2020. So we have seen that all these data sets are basically quantitative. That is, we have some numbers. The heights and widths will be some numbers. The number of road accidents will be some number. The number of the amount of rainfall will be some numbers. But it's a part of data. It's a kind of data. It's called quantitative data. But we also have qualitative data, like the colors of different cars passing through a certain point, or types of diabetic patients in a locality. That is, we know that there are two types of diabetes, type 1 diabetes and type 2 diabetes. So these observations or these data sets are not primarily quantitative. These are qualitative. But as we have, as you may know that statistics is completely a mathematical science. It's based on mathematical techniques. So one need to quantify things or inputs before applying mathematical techniques. So in some way, we need to transform these qualitative data sets into quantitative data sets. That is one of the main building blocks, or that is one of the main ideas of before applying statistical techniques on data sets to extract information. So data may be of many types, say qualitative, quantitative. The distinction between qualitative and quantitative I just made. Then there may be discrete and continuous. So discrete means which is not continuous. So like, see, the number of road accidents. Let us consider that data set. The number of road accidents, that may be like that must be an integer. It cannot be like 3.4 accidents in a particular month, say December. It cannot be possible. So in this sense, it is discrete, that it can take only some possible value that may be finite, that may be countable infinite, but that cannot be uncountable or in a continuous interval. Unlike the rainfall data, which can take any value. Okay, it can take any value. So we do not see, we usually do not see this kind of information that today the amount of rainfall is pi, that is 3.1471, that infinite expansion of pi. That is because that is one of the limitations of the measurement device. But it may happen that the actual amount of rainfall is that irrational number with infinite expansion. But we will round off up to 3 or 4 decimal places according to our convenience. So this is the basic difference between qualitative and quantitative data sets. So this slide gives a basic idea about data. So the concept is much bigger or much vast, but for the timing, this is enough for data. Next, let us understand or study that what is the importance of data, why we need data. So this is actually the motivation of the subject statistics. So for example, I want to go through a certain example based on a data set. That suppose the data set is about height and weight of a group of people. Say n number of people, n may be equals to 100, 1000, anything, or maybe 50. So there are certain relationships in the nature which is completely deterministic. If we know one thing, but just using that deterministic relationship or formula, as we learned algebra in class 7 or 8 or 9, we can evaluate certain things. Like if you give a equals to 2 and b equals to 3, then we know what is a plus b whole square. That must be equal to a square plus b square plus 2ab. Or if we concentrate on this particular example, that suppose the length, breadth, and height of a cuboid is L, B, and H respectively, then without any doubt, without any uncertainty, the volume of that cuboid will be L times B times H. There is no uncertainty. But now let us consider another situation. Let us go back to that height and weight data. Okay. So we know that the weight of a person should increase with his or her height. It is expected because the weight of the skeletal and will increase with the increment of the height. So we expect that the weight should be an increasing function of height. Suppose now the height of that individual is 6 feet. So can we then predict his or her weight? So clearly there is no definite answer to this question, because with 6 feet height, if a person is very thin, his weight may be very less, like 60 or 65 kg. But if he or she is healthy, then it may be possible that his or her weight crosses even 100 kg. It may differ, right? So how it will differ? Now it's our question. We will be concerned with this question. So there are two sources of uncertainties. What are they? First of all, we don't know the form following which the weight increases with height. That is, it may increase linearly, it may increase quadratically, even it may increase exponentially or logarithmically. We don't know about the mathematical form of the relationship between height and weight. Now, the second uncertainty is even more tricky. Even if we know the form, given two persons with exactly the same height, is it natural that they have the same weights? Certainly not. Suppose there are two persons who are exactly 6 feet tall. Can you ensure that their weights will be the exactly same? Certainly not. So suppose, so let us now rephrase this question mathematically, or rephrase this relationship mathematically. Suppose a height of a person is x and the corresponding weight is y. Then we may rephrase y equals to fx plus epsilon, where here f is a function. Okay, so people with high school knowledge of mathematics can surely understand this. But those who are not much familiar with mathematics, so f is a function. That means it's a rule by which the value of x will govern the value of y. So if x is the height, suppose fx equals to say 10x. So suppose x is 6, that is the height. Then fx will be 10 times 6, that is 60. Okay. So the weight of that person y can be evaluated as fx, that is the function of his height, plus some random term. So this function will tackle this this relationship, that is a relationship between height and weight, whether it's linear, quadratic, or non-linear, kind of non-linear. And then the epsilon part is incorporated in this relationship to tackle the fluctuation among different individuals of same height. That is, a person with 6 feet, who is 6 feet tall, may have height 65 kg, may have height 67 kg. This fluctuation will be incorporated by epsilon, will be taken care of by epsilon. So now we have rephrased our problem mathematically, the relationship between height and weight, although it carries many uncertainties. So let us understand those uncertainties. So first of all, we need to observe. So this is the importance of data. So how can you understand the nature of that function f? It may be anything. It may be linear. It may be non-linear. If non-linear, then quadratic or exponential or logarithmic. But how to determine that? Nobody is going to tell me that yes, the height is the weight is exponentially increasing with the height or linearly increasing with the height. It's not. It's almost not. It's impossible to ensure that. Then how can we guess the more or less correct relationship between height and weight? For this, we need to observe data. So suppose, so just consider these two scatter plots. So this is the first scenario where height and weight are almost linearly related. And this is the second scenario where they are non-linearly related and it's a little bit of quadratic in nature, exponential in nature. Okay, so by observing these data and that the scatter plots, that how usually heights and weights of many of a say group of people is related, we have to guess about the choice of f, that function f. So these data, so we are I am using the term data again and again, but the point is that technically in statistics, these observations, that is heights and weights about some individuals, are called samples or sampling units. We do not know about the population, that is the heights and weights of the entire population, maybe of Kolkata, maybe of India, maybe of the world. We do not know that, and it's not possible to collect heights and weights of all the person. It's impossible practically. So we need to collect a subset of the population, and that is called sample. Now, it can be easily observed that the population is unknown, but the sample is known. So the entire statistical analysis will be based on the sample or the sampling units. But there is another component. We have observed the sample, we have collected the sample, that is extracted information about the possible relationship between height and weight. And even from these scatter plots, we may choose a good representative of the function f. But there is another uncertainty. What is that? That if f is so actually there is another uncertainty, and this uncertainty is about f. So what will be the choice of it? Linear or non-linear? If non-linear, then quadratic, cubic, or exponential. So if linear, then this will be the relationship, that is y equals to a plus bx plus epsilon, where x is the height and y is the weight. If exponential, then y equals to a times e to the power bx plus epsilon, that is the error term. But there are many things here apart from the height x, the weight y, and this epsilon term, that is the fluctuation term. Those are what? A and B. So what are they? I will come a few minutes after some slides. So first of all, we need to phrase a good terminology for this choice of relationship between x and y. So technically, the best option to describe the true relationship between height and weight, that is the independent variable and the dependent variable. Here, height is the independent variable because we cannot control it, but based on height, the weight can be controlled. We cannot control it, but it can be controlled. It cannot fluctuate infinitely. So like that. So this is called model. So we have data or sample or sampling units. Then we have model which will feed the data to extract information about that. Okay. So now we have described the mathematical tackling of the function f more rigorously. That is about its shape. But there is another term remaining which has to be taken care of. That is this fluctuation term epsilon. So this was incorporated to tackle the fluctuation between among heights, weights of different people of same height. So first of all, let us understand epsilon, the natures of epsilon. So see, if there are say 10 persons, each one of them have height 6 feet, then it may be possible that there may be a fluctuation among their height, among their weights, but that fluctuation should not be very large, right? Because it can be very large, but in that case, apart from height, there are other reasons which are affecting the weight. This is of course possible in real life, because the food habit is one such factor which can affect the weight, but that needs some other model, and that needs more than one independent variables. In this case, in this case we need two independent variables. One is height and another is the food habit. That is a difficult independent variable to tackle, because that is not quantitative primarily. That is categorical. Okay, so suppose height is the only factor behind it. Suppose it's not true, but for the timing, I am assuming this to understand the statistical methodology, to understand the statistical methodology. So, so epsilon should not be very large. So, so actually, we cannot control epsilon. Okay. So it's a kind of, we do not know the true relationship between x and y, that is height and weight, and we try to reflect it through f. But even after trying fitting that model through f, that may be linear or logarithmic or exponential, we may commit some error. In fact, we will commit some error. And this epsilon is basically that error term which is called random error, because it can take any value, but it is expected that it can take small values of small magnitude, that is, which are close to zero, maybe positive or negative, but close to zero. At least it is expected if the model is close to correct. So randomness means randomness of a variable means it can take any value. And so since epsilon is small in nature, we assume that epsilon takes values in an interval minus delta to delta, which is centered around 0, and delta is a small term, maybe 0.01 or 0.001, like that. So, so since epsilon should take small values, the mathematical nature of epsilon should be like this, that epsilon should take any value within the range, that is minus delta to delta, but it should take values close to 0 more frequently than that of values with comparatively greater magnitude. That is, will move with more chance epsilon should be around minus 0.1 to 0.1, then in the interval that 5 to 10 or minus 5 to minus 10. Now this chance is mathematically called probability, a very glorious field of research in the domain of pure and applied mathematics, along with statistics and theoretical physics. And at least for the last 10 years, it's my observation, it's completely my opinion, I have seen that at least one Abel Prize or at least one Fields Medal has gone to the field of persons in probability. Has gone to the person in the field of probability and its applications. So it's a very glorious field, and it's a very hot field of research now. So mathematically, how epsilon look like? So it's like that. So this is the 0. This is the origin, and epsilon should be concentrated around 0, because it should take small values with higher chances. And that's why this is the chance along the y-axis. The chance is increasing as epsilon is tending to 0 from negative values or maybe from negative infinity. And as it crosses 0, the chance of going epsilon more is going down. So I have used this term density because I am not going to illustrate this because it's a technical, rather a mathematical term. But density means the chance or the probability of taking a value in a very small strip, in a very small region. So this -3 and 3, these numbers are basically very significant. And those who are in statistics or quality engineering background can understand why -3 and 3 are there. Because this is the range of, and not the range, but this is the effective range of normal distribution. I'm not going to illustrate that, but a random normal random variable usually takes value between -3 to 3 with very high probability, like 99 point something percentage. So the error should be like this. And again, this error cannot be controlled. We cannot control this error. So in this model, we have a deterministic component, that is fx, and an random component which is epsilon. If this random component is small, then we will say this our model is good. And to predict y on the basis of the value x, we need to evaluate just fx, and that will be a representative of the unknown y. So here actually this is a very naive example where height and both heights and weight can be measured easily. But there are many things which cannot be measured, like there are many medical parameters which cannot be measured, but they are related on some medical parameters which can be measured easily. In those cases, we may apply this kind of technique. So let us now come back to our main question, that suppose now particular value of the height is say h naught, and we want to know the corresponding weight, that is what can be the weight. So if we know that function f, then fh naught will be a good prediction of that of that unknown weight. But the point is that here, even if we whatever, we may use the linear model, that is y equals to a plus bx plus epsilon, or the quadratic model, that is a plus bx square plus epsilon, or even the exponential model. We have two things which are yet unknown. Those are a and b. These are called parameters, and we need to choose those parameters in an optimal way so that our prediction of weight based on height is good enough. So this estimation is optimal, and we need some objective function to be optimized. Okay, and those objective functions are usually derived based on some physical logics. So let us see one or two examples how these parameters can be evaluated. And the evaluation of these parameters, that finding the best choice of these parameters, is called parameter estimation. So this is actually our model for the n individuals, and these are the error terms. So we need to minimize the errors. This should be our demand. So the sum of all. So we need to summarize these errors. How we can do that? We may take the average or the sum. But the point is that, suppose, let us consider this example. Suppose these are the values of the errors. Then even if summation epsilon I is small enough, that is 1, which is fairly close to 0, some of the errors like -10 or 11 or even -12 are much bigger compared to the total sum. So we need to minimize the summation of some positive functions of epsilon I. Not that maybe epsilon I summation epsilon I square or summation mod of epsilon I or some other positive function. But the first two examples are very basic and very popular in statistics. So this is first example is this positive function is x square, and minimizing this objective function with psi x equal to x square gives the least square estimation. And if psi x equals to mod x is taken, that is called least absolute deviation estimation or LAD estimation. So the second one is more robust. That is, these are not so uh, sensitive to some anomalous observations in the data, which is possible, which are known as outliers, compared to the least square estimators. So we need to collect data. Then we need to first clean the data because there may be some anomalous observations. Then we have to perform some exploratory data analysis tools to understand our model. That is whether uh, linear or quadratic or something like that. And then we need to estimate the parameter based on the sample observation. And finally, we may predict based on the statistical model. This is the effective flowchart of statistical data analysis. But there is another question. So we have described the parameter estimation procedure, but can we ensure that these parameter estimates are in fact reliable? That is, we may rely on these parameter estimates. It may be possible that for a given height of 6 feet, our model predicts that the weight is 180 kg, which is clearly impossible for any human being. 180 kg cannot be a weight of a normal human being, or even some of the uh, human being who have some kind of disease, who may have some kind of disease. It's clearly impossible. So thus we need to ensure the theoretical stability of those parameter estimates and the statistical analysis. Now, this needs sound mathematical knowledge of statistical theory, probability theory, asymptotic statistics, and some deep notions of higher mathematics. So I am not, so as this talk is mainly for general audience, I am not going to discuss those things. We need to study different aspects of mathematical statistics, and most of them are in master's level. So I'm not going to discuss it. I have just given a basic idea of statistical methodology. So this is the basic flowchart which I have just discussed. Next, we have to understand why statistics is a computational science. So we have seen theoretical sciences which starts with some kind of assumptions which are known as axioms, and then develop different mathematical models based on that and based on some outcomes of the experiments. Like, so examples include classical mechanics, quantum mechanics, or say topology, etc. That the last example does not need some kind of data sets, but for classical mechanics or quantum mechanics, that is for physics, we need some kind of experimental outputs to analyze and to build new models. Now, the experimental sciences like industrial chemistry or some fields of biology or medical science, they perform experiments, mainly laboratory-based experiments, and they have huge outcomes, and they then analyze those outcomes to to establish some hypothesis. That is whether uh, smoking causes lung cancer, like that. Now, these hypotheses cannot be proved. We have to support or turn down those hypotheses on the basis of the data. And we need to analyze those data sets. And sometimes these huge data sets are complex in nature, and we need complex models to understand them. And those parameter estimations corresponding to those models are not easy, and in fact they do not obey any closed form solutions. So we need computational paradigms or computational techniques to to circumvent those difficulties. And this actually initiates the journey of computational paradigm of science. Let us understand by two methods, two examples. One is multi-toilo method. So suppose there is a function f on the real line, a real valued function, and we need to evaluate the integral a to b fxd. And we know that for many functions, f it does not obey and closed form solution. Then what we can do, it's basically a random Monte Carlo is a random technique which simulates random variables and take the mean of this function f evaluated at those random samples or random variables to evaluate this integral a to b fx dx. So basically, we may also implement some kind of numerical techniques of integration like Simpson's one-third rule or trapezoidal rule. But Experiments and theory of Monte Carlo methods have shown that these methods have much more accuracy than those numerical methods. And another thing is artificial neural networks. People from engineering or computer science background are surely introduced about this, and I am not an expert of this field. So this is basically, this idea was motivated from the physiological structure of neural networks in human brain or animal brain. These consist of multi-layer probabilistic reweighting techniques to learn about input signals. Now, what is signal? Signal means what a device is receiving. Like we are hearing some sound. This is the kind of signal. We are seeing some kind of light. This is the signal. Or we are reading some information from some book. This is the kind of information. And these artificial neural techniques are mainly focused on classifying and predicting things based on this inputted signal. I am not going to delineate it because it needs probably a separate session or separate talk. Next, I am going to present some of the applications of statistics, some of the applications of statistics in real life, mainly in the fields of engineering and social science and technology. So statistics is almost everywhere nowadays, from business and commerce to science, medical to engineering, social science, and even in literature. Because 5 years back, actually, I read a paper on that a new poetry was discovered in some library of Oxford University, and professors of English, some professors of English have claimed that that was actually written by Shakespeare. And finally, the statisticians from that Cambridge and Oxford universities have come, and they implemented some Bayesian statistical model to understand whether that was written by Shakespeare or not, based on the philosophy that Shakespeare tend to use new words in his literature. Okay, so that was a very interesting example. Even today, read about one I read about one article in Anandabazar Potrika that statistical method can be applied to criminology to detect criminals or criminal activities. So let us first go to the application on image processing and MRI. So how we can visualize a image mathematically? It is basically a map from R2 to R3. That is, it is basically the collection of all the colors in each of the coordinate of that image. And these coordinates are basically, we take it rectangular in nature, and those are called pixels. Okay. And in each pixel, there may be many colors, but all those colors can be composed by mixing three colors, red, green, and blue, with some intensity. Okay, so that's how it is becoming a map from R2, that is the coordinates x and y, Cartesian coordinates, to R3, that is the intensities of red, green, and blue color. So actually, these image processing tools are primarily focused on two tools, that is noise reduction, a method of removing noise from the image that may be taken with some noise, that is hazy, and edge detection, so make it more clear. Okay, so this is one example of a image processing tool where this is a brain image, and this is the reconstructed image after noise reduction followed by edge detection. And this is basically a part of cerebrum, probably the left and rear part of the cerebrum of human brain. And these are very essential in medical science because doctors need to take decision based on these MRI scans. So this is the source of this image. One may find it on the internet. Next, I am going to pattern recognition. These have mainly two tools, classification and clustering. Those who are from computer science background, they know these terms as supervised learning and unsupervised learning. So classification usually deals with, it's slightly easier, and actually they deals with discrimination of different objects which are mixed in a certain place. But classification first learns the classes and then try to predict the class of a new object. That is what some examples are given. see, this ball is red, this ball is green, this ball is blue, and then a new ball is given, and you have the classifier has to predict the color of that ball. But in contrast, clustering is a more difficult thing. There, just the balls are given and no labeling is given, whether it is red, blue, or green. And the clustering device has to find out the number of colors it have and how many of them are them are red, how many of them are blue, how many of them are green. That is, these labels are defined by the clustering device, and it has to essentially make the cluster centers and the predict the cluster centers and the cluster memberships the of the sampling units given. So this is an example of clustering. So these are red. So there are three types of units: this blue, red, and this triangular shaped region. That is triangular. I do not know that whether the color will be visible in the screenshot. So these are the triangular parts. These are the circular points, and these are the rectangular points. These are the three features of that of this cluster, of this mixture. Next, I am going to biological statistics. These have basically three components: statistical genomics, epidemiology, and medical statistics. Medical statistics is slightly different, but statistical genomics deals with the study of gene expression datasets, huge gene expression datasets, and analyze it mathematically, mathematically and statistically for personalized medication or to understand certain complex diseases mainly related to cancers, the different kinds of cancer. Okay, so bioinformatics, computational biology, statistical genomics are some of the new fields in this research track. And epidemiological methods are usually deals with usually model the spread of the epidemics. So we have already seen during COVID-19 that many of the models, many of the people have come up with different predictions that by 2020 December, the number of COVID affected patients in India will be like that or will be like that. So these are basically based on this kind of epidemiological model, and SIR model is among the most popular eminent epidemiological models in the literature. Finally, we are going to econometrics and finance. So this is basically a field which deals with economical and financial data sets. Like some examples include the evaluating the impact of new fiscal measures on the economy, or understanding spatial effect on certain trades to derive an optimal economical policy which will be eco-friendly, like that. So these methods aim to understand the relationship between certain economic factors by analyzing economic data sets. Time series analysis and multiple linear regression and regression diagnostics are among the most used methods by econometricians. Finally, I have reached almost the end of this talk. So nowadays we are familiar with this term data science. So what is data science? What data scientists do? So it's a new field of STEM, that is science, technology, engineering, and mathematics. And data science, although it's based on statistical and mathematical tools, but it is not simply an extension of statistical literature. So it's basically a very beautiful and interdisciplinary field, which mainly based on statistics, mathematics, and sound knowledge of computer science or computing. So data scientists acquire clean structure and analyze, and then finally model the data to identify trends and themes from any kind of data and from huge amount of data, which is being taken continuously by some computing device or some online source like that. But and finally, they generate useful insights and make predictions. They try to generate useful insights and make predictions. But in contrast, statisticians deal with data sets which tend to be smaller than those data scientists, and they are primarily interested in sampling, then find data cleaning, then developing methods, and most importantly, they want to theoretically guarantee the suitability or the reliability of their estimation procedure or the inference. in general by means of mathematics. So this is the basic difference, and the point is that many of the corporate industries now seeks data scientists instead of data analysts or statisticians. So there may be a confusion that statistics will become a new science or technology, and that will be known as data science. In fact, many of the institutes like in IIT Patna or IIT Kanpur or many of the private institutes in India have started courses on BTech and MTech or BTech in data science instead of BSc in statistics. Okay, so statistics, it's I cannot deny that it's a time when statistics is undergoing a phase transition. It is becoming more a technology from a basic science. So in future, we must say that statistics is going to be a balanced combination of mathematics, statistical methodologies, and computer science, which may classify statistics as an engineering rather than a science, where the materials will be the various data sets and the machineries will be the methods, computations, and mathematics. So with this, I conclude my session. Thank you once again. Thanks for this opportunity. Thank you.